So I saw some answers. I'm not seeing answers in the Zoom chat, which is fine. But domain, just like in words, is all the values that X can take on. So if I'm thinking about this graph, then my domain is all of the X values over here, or from 5 all the way out to infinity. Notation wise, if I write this in interval notation, I'm going to use a square bracket to show that I am including the 5. And I'm going to use parentheses because infinity is not like a specific number that we can get to. So we're always going to use parentheses with either positive infinity or negative infinity. In terms of the range is all of the Y values that the graph covers. And since the lowest Y value on the graph here is 3, and it keeps going up forever, that range is going to be 3 to infinity. Again, the 3 is going to get that bracket because we are including the 3, and the infinity is always going to have parentheses wherever it's showing up. So if I do another quick one where I give you the picture and you write the domain and range, let's give that a shot. And then we'll talk about, well, what if I don't have a graph? So let's say that my picture looks like this, and that's some sort of parabola. What's the one point on the parabola you would really like me to label right now in order to find the domain and range? Totally. So let me go ahead and label that vertex, and I'm going to say that that is 1, 4. That's the point for my vertex. So go ahead and write the domain and range on your paper for this guy too. Or if you're on Zoom, you can always type your answer in the chat. See some answers walking around. So if I'm thinking about the domain here, domain is all of the values that X can take on, which means I'm going all the way over here, negative infinity out in that direction, positive infinity out in this direction. There are no X values that create problems. So I can write that as negative infinity to positive infinity. If we wanted to get fancy with it, I could write X is an element of the real numbers. And sometimes that's the notation that our book will use. You do not need to use the fancy notation, just wanted everybody to have seen it. In terms of the range, again, thinking about Y values, our lowest Y value, these are both headed down to negative infinity. So my Y values go from negative infinity all the way up to 4. Good times. Now, most of the time when we're being asked to do domain and range problems, we probably won't have a graph, or we won't know what the graph looks like necessarily. So we need to have some tools for how we're going to deal with domain and range, even when we don't have a picture to go with. So there are really only 3 rules for domain, and it's the same 3 rules that we are going to use now and in 16B and in 16C if you're hanging out that long. I know not everybody needs to take the entire calculus series, but there are really only 3 things that can go wrong with domain. So if I put this out there, when we're thinking about domain, I can't have a what, where. How many people think a 0 below? I can't have a 0 in my denominator. That's definitely one of the things that can go wrong with domain. So I'm just going to write that as like a number divided by 0. No, can't do that. What's another thing that can go wrong domain-wise? And I'll give you a hint. The very first thing we graphed. What can I not put inside of a square root? Totally. So I'm just going to write that as I can't have a negative inside of a square root. Fun fact, cubed roots are fine. It's only the even roots that are a problem. So if I had the cube root of -8, this one's okay. Because -2 times -2 times -2 is equal to -8. So cube roots of negative numbers are totally defined. We're totally good with cube roots. It's only those square roots. There's one last domain issue, but luckily it's not going to come up for you, or it shouldn't come up for you until 16b, when you're talking about log and exponential functions. But just for completeness, I'll put it on here. If we have a log or a natural log, I can't have a 0 or a negative inside of that. Score. And thank you for people on Zoom who have already put answers in the chat. People in the room, I didn't have a chance to walk around and look at your papers. And people have something written on your papers. Yay. Okay. So here, I'm just going to show you what I would do. It doesn't have to be what you would do, as long as we all got the same answer. When I look at 9 minus x squared, I'm going, oh, hey, that's a quadratic. I wonder if it factors. Sure does. I've got 3 minus x times 3 plus x. I need that to be greater than or equal to 0. I've got 2 solutions there. The x could be 3 or x could be -3 to make it actually equal to 0. Then I would draw a number line, put -3 and 3 on it. I'd pick some test points to plug in. And I'd be like, oh, hey, well, when x is 0, if I plug in 0, 9 minus 0 squared, yeah, that's greater. That's positive. We're good to go. If I plugged in something over here like 4 squared, 9 minus 16, that's negative. We can't use that part over there. If I plugged in a test point over here like -4, -4 squared is positive 16, 9 minus 16, we're negative again. So this is the piece of it that we want. My domain is going to be from -3 to +3. This number line trick, it's useful in a lot of places for us in calculus. So if it's not something that you are familiar with, 1, I promise we'll get more practice with it. But 2, it is a tool that I'm going to reach for in my toolkit a lot. I didn't ask us to find the range of this thing, but we could. Now for range, there are really 3 options when we're finding range. The first one is to sit back and look at it and just think to ourselves, what sort of y values can we get out of this function? Another great option would be to graph it. The third option that we sometimes have is finding the inverse of the function. For this particular one, I'm going to go with graphing it is definitely our best option for finding the range. Does anyone know what this is as a graph? So I saw some people waving fingers around in the air, being brave, trying to show me part of a graph. This thing is half of a circle. It's the top half of a circle. How the heck do I know that? Well, this function shows up a lot. But if instead of writing f of x, if I were to write that as y, so that I'm looking at y is equal to the square root of 9 minus x squared, and then I squared both sides, and then I added the x squared to both sides, that I'm guessing you might be able to look at and say, oh, that's the equation of a circle. That's a circle that's centered at 0, 0 with a radius of 3. So this would be like the whole circle. The problem is that that square root piece, the answer of what comes out of a square root is always a positive number. So that square root piece tells me we're only looking at the positive y values or the top half of this circle, and the rest of it should not be included. So my range is from 0 to positive 3. There are only 3 things that are ever going to go wrong with domain. I can't divide by 0. I can't take the square root of a negative. I cannot take the natural log or the log of a negative number or a 0. Well, in this case, I'm looking at it and saying, oh, I've got a fraction. So automatically 3 minus 2x cannot be equal to 0. That's it. I don't care what's on the top of a fraction. The top of my fraction can be equal to 0. The top of my fraction can be positive. It can be negative. The only thing that matters is that I can't have a 0 on the bottom. So if we rearrange this, looks to me like x is equal to 3 halves, or rather not equal to 3 halves. And maybe we can leave it like that. If we needed to put that into interval notation, then in interval notation, this would look like negative infinity to 3 halves, parentheses, union, 3 halves to positive infinity. Like, why can't I put in 3 halves? So if x is equal to 3 halves and I stick that in here and I try to find what f of 3 halves is, that would look like 5 times 3 halves divided by 3 minus 2 times 3 halves. So in the denominator, when I start working through the numbers, the 2 over 2 is going to cancel here. On top, I'd have 15 halves. And on the bottom, I'd end up with 3 minus 3. So now I've got 15 halves divided by 0. And that's the problem right there. Is there's only one y value that we never touch on the graph, and that's the negative 5 halves. So to leave that out, I would write that as negative infinity to negative 5 halves, union, negative 5 halves to positive infinity. And that's going to be my range. In terms of domain, I have 2 things that could be a problem. I know that I can't have a negative inside of my square root. So already I know x plus 3 has to be greater than or equal to 0. But I have another thing going on, and that's that I can't have the bottom be equal to 0. And I need to take into account both of those things at the same time. So if I think about that x plus 3 being greater than 0, Well, that would say kind of on my number line that I've got -3 and I need the side that's greater than -3. But that x squared minus 16 says that x can't be 4 or -4. Well, I don't have to worry about the -4 because it's not even in the part of the number line that I would use based on the top, based on my numerator. But I also can't include +4. So it's like I have to come over here and punch a hole out at 4. So putting that together as a domain statement, that would say I'm going from -3 to 4, union 4 to positive infinity. There is no way anyone is asking you for the range on this problem, unless they are explicitly giving you a picture of it. No one is asking you for range on this problem. It's messy, but the domain question is fair game. There is a lot going on in that thing I just wrote. And the first thing that I want to do is just practice how we would read this notation. Oh, and I should give you a second. I know people are copying down the graph, so I will pause myself for people to copy the graph down. One advantage of Zoom, the screenshot, take a screenshot, you got that graph already. So looking at this, the way that I read this notation wise, those 3 letters LIM stand for limit. So this says the limit as x approaches. And then here's where the subtlety comes into play. This part says -1. And this part we often read as from the left. I prefer to think about it as from a little bit less than -1. But standard would be to think about it as from the left. So Isaiah has given us a roly-poly as our example. And so what this limit means to the roly-poly is walking around the graph on the left-hand side of -1. That roly-poly has teeny tiny little legs. So he's walking along with his teeny tiny little legs, walking along. Says, oh my goodness, I'm getting close to -1 on the x-axis. Looks over at the y-axis. What does he see? 1. So the answer to a limit problem is always, what is the y value trying to be? Now, a really similar looking limit, but with a different answer, would be if this said the limit as x approaches -1 from the right. And I read that plus after it as from the right. So now our roly-poly friends has started out on the right-hand side of -1. They're walking along with their teeny tiny legs, walking along, looks down, says, oh, I'm getting close to -1 on the x-axis. Look at the y-axis. The number that I see is 3. And the answer to a limit problem is always just, what is y trying to be? So looking at my lovely graph here, I'm gonna have you do a couple of limits on your own on your paper. So let's take the limit as x approaches 4 from the left and the limit as x approaches 0. Yes. I did not give us an equation for that function. I've only given us a graph, so we have to use the picture. So we'll see if this works. Show me on your fingers or type into the Zoom chat. What do you get when you take the limit as x approaches 4 from the left for this function? No one typed it in the chat either, and I'm realizing that there's probably a reason. Because I didn't label something on my graph. Let's try that again. Now that I've labeled things on my graph and given away what the answer is. The limit as x approaches 4 from the left. What's the y value trying to get to if I'm walking along the graph? Now there is a thing that's equal to 3, but the thing that's equal to 3 is f of 4. And that right there is really at the heart of what's happening with limits. So when we're thinking about limits, we're moving along that graph. What's the y value that we're headed towards? Imagine you're the teeny tiny roly-poly. You can't even see this spot up there floating in the sky. If I'm just moving along the graph, the y value we're heading towards is down here at a y value of -1. By the way, for this particular limit, I didn't ask you to go from the right-hand side, but if we had, we would also be headed towards -1. If I approach 1 from the left, then coming from the left-hand side, the y value that we're getting close to is 2. And if I'm coming from the right-hand side, the y value that we're getting close to is 0. And -3 from the right-hand side means I'm coming from over here, and the y value we're getting close to is 3. Now, if I wanted to ask you, which I could, many of the problems in the textbook do this, f of -3, the value of the function at -3 is +3. F of 1, the value of the function when x is equal to 1 is 0. Because that's the side with the filled in dot. Now, so far, the limits that I've been asking about have pretty much all been given you a left or right-hand side to approach from, but I don't have to put the plus or minus after it. So if I had written the limit as x approaches 1 of g of x, there is no limit. We only define the limit as I approach a number if I'm getting the same value from both sides. So here, when I think about approaching 1, and we often write DNE for does not exist. So if I don't get the same value from both sides, then that limit does not exist. Yeah. Yeah, we're always going to find the closed circle. And if there is no closed circle, then we would say that the value of the function was DNE. Yeah. Okay. I think it's time to ditch the pictures and do some limits with equations. Yeah. So these two don't match. If you can just plug in the number and get an answer. But it's always the first thing that you should check. So when we're doing limit problems, check first. Just plug in the number. Well, in this case, if I plug in 1, I'd have 2 times 1 plus a 3 on the top and 1 minus 5 on the bottom. I get 5 over -4. And you know what? We're done. This is the answer. This is almost never what's going to happen when you're asked to do a limit problem. Something like this is way more likely. Let's look at the limit as x approaches 1 of, go with x minus 1 over x squared minus minus 2. That's not what I meant. I'm just like having a moment here. Let me fix this and make it easy on myself. And then I'll give us a slightly messier one. I'm going to keep life real simple and just do that. So the first thing that I'm going to try with any limit problem is to just plug the number in. But what do we get when we plug in 1 on the top? Totally. Now, if you get 0 over 0, this is whispering to you. Go do some algebra. So if you plug the number in and you get 0 over 0, just imagine that this problem is talking to you and saying, go do some algebra. If you took calculus in a previous life, don't do calculus to it. You won't get points. We have to do algebra to it. That's what we do when we get 0 over 0. Now, there are a couple of different flavors of algebra that come up. Factoring is usually our first line of defense. Since the bottom happens to factor, I can now look at that x minus 1 over x minus 1. And that's going to be a big old 1 on top. I'm going to write out an extra step that you don't actually have to write out, but I'm going to write it out because I can, in case it's helpful. So I've done some algebra to this. I'm now left with 1 over x plus 1. Now I can try just plugging the number in. And when I do that, I'm going to get 1/2. Now, if you're curious, this tells me that if I were to graph this, this graph is equivalent to this one, but there's a hole when x is equal to 1. And the y value for that hole is 1/2. We got time for more algebra? More complicated algebra? More fun algebra? I don't know. But let's take a look at the limit as x approaches 4. And how about, I've got 1 over x plus 1 minus 1/5 all over x minus 4. So the first thing that we should try with any limit problem, and you might even just do this in your head But the first thing that we would try with any limit problem is to plug the number in. And I will tell you that most of the interesting limits in life are 0 over 0 kind of limits. That 0 over 0 is telling us, go do some algebra. But this time, factoring is not going to do it for us. But we are subtracting fractions on top. And whenever we're subtracting fractions, I know we need a common denominator. Should I do the common denominator part, or do you all want a minute to try it? You're going to try it. Okay. You all try that common denominator. I don't know if everybody wrote out that intermediate step. It's okay if you didn't. What we do want to make sure is that because we have that subtraction on the top, we do want to make sure that that subtraction gets distributed to both the x and the 1. Now I'm going to kind of flip this around a little bit, because dividing by x minus 4 is the same as multiplying by 1 over x minus 4. So on top, I've got 5 minus x minus 1, or 4 minus x, and that 5 times x plus 1, and then that's being multiplied by 1 over x minus 4. There are a couple of different ways to finish off the algebra here, but that 4 minus x over x minus 4 term, they almost cancel. They're just going to leave us with a negative 1. You can also get there by thinking about factoring out a negative 1 from 4 minus x. And now I'm ready to plug that 4 in. And if I do, I'd have negative 1 over 25.